started using Google Meet, and I'm not quite sure when we will go back to in person or what the next schedule is going to be. I've sent a couple emails out how the meetup landscape has just changed a little bit, so I'm still trying to navigate what that really means. Um, so before we get started, I just wanted to do a quick, here's a little overview. Is my slide changing, Chandler, or is it not changing?
I do not see it changing.
That's weird. This is... Now it is, right? So I'll let Chandler kind of go in a little more details about his talk once he gets started. But I wanted to introduce Chandler. So Chandler is he's the CEO of a company. How do you say it, Chandler?
Axolotl.
Axolotl.
Yeah.
He provides innovative initiatives in developing aerospace telemetry, analytics, and computer vision applications. Chandler previously spoke at the meetup, I think about a year and a half ago, or maybe it was last year. So he's a return speaker, and I think he can speak a lot to the work that he's doing. They do have a website if you want to check out his company website. But with that, Chandler, I'm just going to hand it over to you, and you can kind of do your introduction and do your slide deck if that works.
Yeah, absolutely. Thank you, Jason. So yeah, as you mentioned, I'm the CEO and founder of a small business, Axolotl LLC. We're a service-disabled veteran-owned small business. I served in the Marine Corps back in 2013 to 2019. When I got out, I had transitioned into software development, and then eventually into data science. Where in data science, I've worked mostly in research facilities, helping support innovation across everything from looking at mortality rate in clinical trials to space telemetry analytics for anomaly detection in asset behavior, computer vision for unmanned surface vessels. Those kinds of things were at all projects I supported for different companies. And then after I got my master's, I decided that I wanted to strike out on my own. I participated in a research project with the Federal Aviation Administration, specifically targeting telemetry maneuver analytics for rotorcraft and how that could impact pilot training at large. So, how do we use data and use AI to help kind of shape the landscape in which we are training people to identify and recognize the behavior of their aircraft during flight operations, and then obviously that extends into maintenance. And as you continue to fly, you're obviously going to have more wear and tear on your aircraft. So what does it look like when you're performing your first S-turn, which is a maneuver that they produce during their training pipeline? What's it look like the first time you do it versus what does it look like the 338th time you do it? So obviously a lot of time series pattern recognition involved in that. And then the computer vision applications that we're building all center around airborne object detection. So as you're up in the air, whether it be a drone, a helicopter, aircraft, a fixed-wing aircraft, jet, as you're up there, there's obviously things like collision avoidance. You're looking at engine safety. So if you have flocks of birds or anything like that, you want to be able to detect them. Hopefully, give your pilot enough time that they can react and change course or make any kind of adjustments or modifications. Today, we're actually going to be speaking about a topic that is something new for us to kind of dive into. So and I'll go ahead and share my slides here. And then, Jason, can you confirm that you can see the slides? Just
yes. And one thing I forgot to mention also, Chandler, is if anyone has any questions, you can type it in the chat. Or there's actually a QA. If you look at the bottom right of Google Meet, there's what looks to be like a couple puzzle pieces that says activities. If you click on that, then Q&A, you can actually enter questions there. But we'll be monitoring the questions as we go along. So go ahead, Chandler.
Yep, thank you. So for this topic, what we're actually looking at is a kind of a translation from a tool that I developed specifically to identify pattern recognition of maneuvers in aircraft behavior. What we hypothesized was that we could do the same thing for satellites. So obviously, when you look at the behavior of an aircraft when you're performing certain types of operations, you're going to have trends and patterns that kind of allude to what is being done with the aircraft. For instance, the first time you learn how to park your car, parallel park your car, when you're told to turn your wheel one direction and told that if you turn it in one way, it's going to go the opposite way, all those kind of nuances are actually reflected in the component behavior of your car. So if you had data recorders that were identifying, what's the angle turn of your wheel, what is the acceleration, all those kinds of different values that you could be collecting off of your car while it's in transit. Those would all help kind of build out what is a parallel parking maneuver actually look like in terms of the data that's generated. So with an aircraft, if a pilot takes off and it goes into their regular flight pattern and they're holding steady at a certain altitude, and then they're told, all right, we want you to conduct an S-turn, that S-turn is going to have reflected behaviors in the data that we can kind of point to and say, okay, this is what that pattern consists of. So if they conduct an S-turn, it should look like this in the data, which obviously helps us out with a lot more various different tasks, specifically if you're talking about anomaly detection or if you're looking at predictive maintenance. So if you're going up and you're conducting an S-turn, we know that the aircraft is going to be operating with a certain detect black hole. Not quite. But we expect that it's going to be behaving a certain way, that it's going to have certain indicators in the data that are going to tell us, hey, this is an S-turn. And then obviously once we've seen enough S-turns, we can tell you that if something is outside of the normal behavior of an S-turn for that aircraft. So it could be that the pilot is, pushing the throttle down too far, the angle of the nose of the aircraft is too low, things like that, that would be considered out of band for what an appropriate maneuver would be. Obviously, all of those things were to deal with our aircraft. When we were starting a project for a competition for the spacecraft, what we kind of looked at was what were types of maneuvers that a spacecraft would be conducting. This video here is just a quick snapshot of our telemetry tool. This is called Telemap. It's Telemetry Maneuver Analytics and Positioning Platform. It has three basic components, or the main components that go into it. So it does the flight maneuver recognition, which in this case, as you can see in the video that's playing here, this is for a rotorcraft. It's identifying two distinct types of maneuvers that occurred, one of them being a turnabout of point, the other one being an S-turn. You can see in the video that you're able to click maneuver. You can edit these points. That allows us to go through and do augmented learning. So as we continue to train these models, the feedback that we get during the initial run through of a model helps us identify how well it's performing, and then we can make adjustments. So you can remove false positives. So if something is detected that is not actually a true maneuver, or maybe it's incorrect in terms of the label, you can make those adjustments. You can also adjust the start and end values of those, and I recognize that the video stopped playing. So you can make the adjustments on the produced labels, which will then go back into the learning process. What this allows us to do is continuously learn from the professionals and the domain experts that are using these tools and software, so that our models are continuing to improve and be more useful. Aside from the maneuver recognition, it also has anomaly detection. So anomaly detection is pretty straightforward. I feel like most people are familiar with the concept of anomaly detection. You have expected behavior patterns based on what types of operations you're conducting. Anything that extends beyond that and deviates from that expected pattern would be considered anomalous. This can be used to start identifying things that are environmental anomalies, user-based anomalies. So, for instance, for an aircraft, if a pilot is producing an anomaly through some action that they are performing, this tool would be useful in helping determine what that is. And then also for a spacecraft, operator is going to be issuing commands to the spacecraft, but there's also going to be environmental factors such as the third body effect of the sun and the moon on the aircraft. All of those different things that are going to play into it, we can kind of identify where those behavior changes are occurring and then characterize them. The last major component in Telemap is a generative AI component. Specifically, we use a combination of sequence GANs, generative adversarial networks, to help supplement one of the biggest issues that you'll obviously have with any kind of task like this for pattern recognition is that normal behavior or normal operation, those value points typically greatly outweigh the labeled instances of either your desired patterns of detection or the true ground truth anomalies that you're looking for. So when we do have those available to us, we need to supplement them somehow. So we have baked in a few different sequence GANs to help us generate these representations in these very complex multidimensional arrays to help be more specific in terms of what we're generating. So it's not as something as generic as SMOTE or any of these other upsampling type techniques. It's more specific to the maneuvers that we're actually trying to identify. And I will go to the next slide. So for space asset maneuvers, it's a little bit different and a little less complex to visualize than an S-turn or turnabout point or all the different types of maneuvers that an aircraft pilot or a rotorcraft pilot might be conducting. Typically, when we think of a satellite going up into the sky, they're launched, we expect them to hold orbit, whether that's in geospatial, geostationary, or LEO, low Earth orbit. We expect it to hold the orbital path, and the only really deviations that it should see are things that occur based on thrusters being applied to help it maintain the optimal orbit, or if it's got a collision avoidance system that helps it move away from debris. That's more common, especially with like low Earth orbit objects. As you can imagine, with the sheer amount of things in low Earth orbit and all the debris that exists, it's a little bit more frequent that something might have to adjust, its path, its trajectory to avoid colliding with another satellite or just debris. But geosatellites are typically going to operate under station keeping behavior. This means they go up, they maintain their orbital path that is designated as their optimal orbital path so that they can continue to provide uninterrupted communications or services based on whatever their functioning purpose is. They have various different propulsion systems that help them accomplish that. The image here on the right is an example of an electric propulsion system. It uses two arms that help it kind of navigate which directional propulsion it needs to apply. Typically, when you look at propulsion systems, they're designated by either east and west or north and south in terms of the orientation and directionality of the propulsion system. But all these are meant to do is help it maintain orbit. It's not supposed to allow it to move across orbits or anything like that. It's not used to, directionally steer, counter orbit, or anything like that. It's purely meant to help it maintain its designated optimal orbital path. Now, as I'm kind of mentioned earlier, there are effects that can be applied to a satellite that will cause it to deviate from that orbital path, and this isn't necessarily a nefarious thing or something that happens that scientists can't figure out or anything. Like, this is a very well-known thing. That's why these thrusters exist. But third body effects from the sun and the moon are going to cause an inclination drift, and we'll kind of talk a little bit more about what inclination is here in a little bit once we start looking at the data. But it causes an inclination drift, and that is going to change the positional path of the satellite. So the north and south propulsion systems are used to apply corrections, keep it in that path, but that's obviously going to have some kind of reflection in the data. So when those propulsion systems kick on and it pushes it back into where its alignment's supposed to be, we should see that pattern reflected. Variation in the Earth's gravitational field, as well as solar radiation pressure, are going to be what cause the deviations that the east and west propulsion systems seek to correct. And the reason why I'm kind of explaining these different propulsion directionalities is that when you look at data sets for satellite telemetry, one of the common things that you have to do is you have to separate it out based on directionality, because the patterns that are exhibited for one type of maneuver in one directionality will be different than those produced for that same maneuver in a different directionality. And we'll kind of talk about the different maneuvers that we're going to be looking at here in just a second. When you are looking at why it's important to kind of identify some of these maneuvers, one of the main things that everybody always says is, okay, yeah, it can do the thing, it can move left, right, you can get it back onto its orbital path, but what does that actually mean? Why is that important? Why can't a human just sit down and do that? Truth be told, human absolutely can sit down and do it. That's what we've been doing for, since space technology existed. We have some kind of human validator that goes in. An operator issues these commands to tell the satellite, hey, you need to move this way, that way, apply this directional thrust. There's obviously a degree of automation that's been applied over the last 2 decades to help kind of augment the manpower limitations that we have for people that are trained to do this. But more to the point, we're getting to a level of density in GEO and LEO orbits where there are too many space assets and too many directional anomalies that are occurring that we don't have enough people to kind of identify those in a timely manner and then be able to apply corrective measure. So it's not so much that humans can't do this; it's just that there's too much. There's too much quantity for us to be able to do in a timely manner. Now, some of the things that I like to point out to people in terms of kind of buy-in whenever we talk about launching a full bus. So obviously, I'm not talking about a small CubeSat here. These are typically larger satellites operated by groups like SpaceX. GEO satellites, they're going to cost quite a bit more money to launch than LEO satellites, and there's usually less variation in the types of satellites that you can launch for them to be able to go out in operation for an extended period of time. So the average cost to launch a new satellite can range anywhere from 50 million to 500 million. The 500 million mark, you're usually launching multiple satellites in one launch, typically with a shuttle assist. But 50 million would be approximately where you'd be looking at trying to just launch a singular satellite into GEO orbit. Now, the collisions that occur in GEO are going to be less frequent than some people might think, or if you didn't think previously about how often does a satellite collide with either another satellite or some kind of debris that is out in its orbital path. It really only occurs about once every 4 years. It's quite a rare occurrence, and typically it's a much smaller debris object that impacts these satellites. One of the things that's been occurring more frequently with GEO satellites is that their lifespan cycle for the predictive maintenance has been impacted to where you'll have loss of coverage of a given area because the satellite in geostationary orbit has essentially an area that it is responsible for. And if that satellite goes down for whatever reason, which could be end of life cycle, or it could be some kind of anomalous event that has brought it out of commission, you're going to lose coverage area in that specific location until other trajectories can be modified to account for that loss. And that is still very much a manual process. If a satellite gets brought out of commission unexpectedly, they have to reroute and kind of fill in the gaps, manually through various operators working together. Collisions in LEO are much more likely. They're much more frequent. There's approximately 1,600 close calls every week, according to SpaceX. In terms of actual collisions, about 50% of those end up with actual collisions. They can be anything from an actual satellite colliding with each other, which when they collide with each other, they kind of just burst into small pieces and then either get added to the amount of debris that's circling the Earth, or they burn up in the atmosphere upon re-entry. That's why we don't really notice it as regular terrestrials just sitting down here on the Earth. But it does happen pretty frequently in low Earth orbit. With us monitoring the component behavior and the actual maneuverability of these satellites, what we can do is we can maximize their lifespan. So as I mentioned, it is kind of costly to get one up there. The nice thing about GEO orbit is that they typically last a lot longer, so they can range from anywhere from 15 to 20 years. However, if we are doing proper monitoring, looking at maintenance scheduling and all that kind of stuff, or even informing what our replacement schedule should look like, we can maximize the lifespan, or at least reduce the loss of coverage and loss of functionality when something does go down. It's been shown that proper monitoring can extend the lifespan of the satellite an additional 5 years, especially if it's something that is accessible for either refueling or maintenance, from a different craft. So the data set that we were working with was actually provided by the MIT's Astrodynamic Space Robotics and Controls Lab, or the ARC lab. This was part of a open competition that occurred back a few months ago. Started in December of last year, or we started in December of last year working with them for this competition purpose. Their goal was to detect specific types of maneuvers that occur with these various different satellites. They had quite a few different types of satellites, but they were all geo satellites. There was approximately 500 simulated trajectories that they were working off of for these various different satellite types. They have a really impressive high fidelity simulator that was able to spin these up. There's obviously, nothing's perfect with simulated data. So there were obviously a few instances where feedback was garnered to identify the correctness of these trajectories. But the idea being is, since we don't have a huge access to, or a huge public access, or even proprietary access to historical data that allows us to build out these pattern recognition models, simulators like this are a great way to kind of fill that gap. So what they did is they spun up trajectories through simulation for 6 months for each satellite. They had the data binned in 2-hour intervals, and the target labels of these maneuvers that they were working with predominantly revolved around 3 nodes: the adjust drift node, which is abbreviated as AD, initiate drift, which is ID, and then the initiate station keeping, which is IK. Now, they also included different propulsion types. What I noticed while working with the data, so the different propulsion types, they had chemical, electrical, and hybrid, which would be just a combination of chemical and electrical. For the different propulsion types, the data was much less informative as to which propulsion engine was being used, or which propulsion type was being used. Identifying nodes was relatively successful across the board, from everything from their original random forest model that they had started working with, all the way through to what we started using, which is a bidirectional or convolutional bidirectional LSTM network, which we'll kind of walk through here in a second. Being able to identify the pattern of life nodes specifically. So for when something is initiating drift, that means that it is the propulsion is being applied, or the propulsion is not being applied. The third body effect, or some external effect is occurring that is causing the satellite to drift. Adjusting the drift is some kind of propulsion maneuver to help it shift away from its naturally occurring drift. And then the initiate station keeping is how it gets back into what is considered its normal operation. So you have essentially 3 different types of functionality that are occurring in the data that will be representative, or should be representative, in the patterns that you're observing. If you remember, I said inclination and eccentricity were the 2 primary values for what we would be looking at, depending on if it was east-west or north and south. So it really comes down to which directionality we're looking at for where this maneuver occurred. The data set itself was broken down into east-west and north-south for each of the satellites, so we would separate them out. This is a sample of what the raw telemetry looks like. Obviously, it's just a giant table here, but I didn't want to overwhelm anybody with this. However, the timestamp you can see over here, this is for 1 satellite, and this is 2 days worth of operation. You can see that on the timestamp, it starts out for the 1st of September of 2022, and then it goes in 2-hour increments and just increments out through. That is the continual pattern that occurs with the data as you continue to look at the entire 6 months worth of operation. So every day for 6 months, we have 12 records. You have various different columns here that are applicable to the pattern recognition. So one thing I did want to highlight is obviously not every column here goes into the modeling effort. So things like latitude, longitude, altitude don't get really applied to our pattern recognition. We stuck with our measurement variables for things like eccentricity, inclination, argument of periapsis, true anomaly, and then obviously the X, Y, and Z, and then also the velocity of those. There were very few external resources to, again, kind of apply to the modeling effort that we were looking at with this data. And in most cases, when you're looking at satellite telemetry, it's going to come down to the fidelity of either the data recorder that you have or the simulator that you have. Some simulators are capable of simulating down to a very small component level. So for instance, you could have a single thruster. You could have measurement values that relate to that single thruster's behavior. You could have everything up from the entire bus, which this would be from the satellite bus itself, or you could have somewhere in the middle where it's smaller components, but they're much more defined, like a reaction wheel or something like that that is responding to an event. So depending on what kind of data you have available will also dictate your approach with this.
Hey
I do want
Chandler,
to take.
there was two questions. If you saw them, did you want me to read them? There was one question about what about a station change is that accounted for, and then the question was what units are the X, Y, and Z in?
Yeah, so the station change in terms of by station change, do you mean from its orbital station, Chris? Oh, to cover outages. So no, for the purposes of this demonstration and the challenge that they were working with, it was purely based on detecting existing maneuvers that are just standard maneuvers, not in response to any kind of coverage reallocation or anything like that. In a real world scenario, what you would look at in that case would be if something did go down, like if in a simulation environment, if you did have one satellite go down, you would look at what is available to be maneuvered optimally, and then what kind of maneuver actions would need to be taken to continue to maintain continuous coverage without any loss of service to that area for where that satellite is pointed to. And that would be an extension of this. That would obviously require fine tuning, and you'd start looking at discrete event simulation to kind of map out what is the best route for that. And then all of X, Y, and Z, these should be in degrees that were for the I want to say it was meters per second. That was the unit of measurement. Okay. All right. So from that data table that you saw, so essentially we had raw data. So again, it extended all the way through to where we had sorry, not I didn't mean degree, I meant meters per second. But I can also get confirmation for you towards the end. So from the every day for 6 months, we had 12 records. Essentially, the path forward was a determination on how do we identify the most amount of patterns, correctly, because the false positive rate for like just a standard, one row for every one label for every row, you're going to get a lot more station keeping behavior because that is the normal behavior. So you create a very highly imbalanced data set just right off the bat. You're going to have upwards in the hundreds of millions of records for station keeping behavior, and then for actual maneuver nodes, you might have like a couple hundred. In fact, when I first broke it out, there were around 500 nodes that were actual maneuver nodes, and then everything else was either station keeping or it was not station keeping, but it wasn't the actual maneuver itself. In the challenge, one of the things that they had done as part of their dev kit to help people get started was they forward filled. So if a maneuver had occurred, they forward filled until the next maneuver or until the end of the time series collection. So if it was initiate station keeping, then it would be forward filled until it reached that station keeping behavior, and then it was reapplied to the station keeping normal label. If it was a just drift, then it would, every record, subsequent after the adjust drift node would be forward filled. The labels would be forward filled as a just drift until it reached the next node, which could be initiate station keeping, or it could continue on to the end of the series. So with that, it does help with the imbalance of the data set, but then you're looking at nodes that are not specifically the maneuvers that are occurring. They're a byproduct of the maneuver, right? So they might have similar characteristics, but you're going to have a lot higher concentration of false positives based on the fact that you're looking at data points that are either its return trip to normal station keeping behavior, or it's somewhere in the in-between space where there might be a little less significance to the pattern that's being observed. And when you're looking at doing pattern recognition, you want to try to maintain the integrity of the patterns that you're detecting so that you don't get a lot of cross-pollination with other patterns or other behaviors that might trigger false classifications of what's occurring in that instance. So our approach was a combination of some segmentation work that we did that allows us to take in a raw time series and break it down into various windows of overlap. With their presentation of the challenge, since it was 6 months worth of data for each satellite, at first we wanted to go very granular. We wanted to say, let's do windows of like 4 hours at a time, and then have it overlap. For every 4 hours, you have a 2-hour overlap, which would create a pretty consistent spacing, so that you're not really letting any data points slip if a pattern occurs at the end or beginning of one of those segments. However, what we noticed was that obviously with 500 different satellites with 6 months worth of data, that quickly gets out of hand with how many segments you're looking at, and the real trade-off there is not you might be 1 or 2% more accurate in the patterns that you're detecting, but you're eating up RAM, you're eating up processing time because it has to create the segments. And then it has to obviously do a lot of trimming for the tail segments. You create forward and backward so that you don't miss any of the data points. And if something is caught on the end, you might end up trimming it off. So instead, what we did was we settled on going a day at a time. So since it was already broken out in that daily kind of collection with 12 records per day, we created our segments around each day. And then we overlapped in the midpoint for the day. So each day has 12 records. There would be an overlap of approximately 6 records as it moved from segment to segment, so that we could get most of the values for a day into one segment and then not lose out if something occurred later in the day or early into the next day. This is a just representation of our modeling that goes into the background of it was originally our flight maneuver recognition model architecture. We did make some adjustments and some tweaks specifically based on feedback that we got from the model when working with the satellite data. Obviously, one of the biggest things that you look for is you want to have a good framework, a good starting point with your neural network to kind of build off of in terms of how well it performs, what kind of segmentation it's working well with. And then if you're able to identify some of the more complex patterns, then typically on the easier patterns you're going to do okay too. That was the mindset that I went into this with. I was identifying an S-turn and a turnabout a point to me seemed a lot more difficult of a challenge because the start and stop points were so irregular. You could kick off a turnabout a point at any point, and then you could continue to make turnabouts of points 3 or 4 times in a row. Whereas with these maneuvers for these satellites, they're going to have specific kickoff events that occur at specific times. There's obviously heuristic-based approaches that you can go look at for how satellite behaves or satellite behaviors are measured. So they're very calculated. And I know everybody says it's not rocket science, but rocket science, satellite science, I guess. But there's very specific things that kick off these events and how they're measured and what they mean for the behavior of the satellite. So I expected that the patterns would be somewhat easy to detect and identify. So I didn't change my modeling architecture too much. But what I did find was that, for instance, in some of the convolutional layers, the feature extraction that was happening and the feature importance that was being highlighted would drown out a lot of the data points. And then if something was, something was odd, like in one of those in-between phases that I mentioned, where it wasn't quite a maneuver, but it was on its way back to a normal station keeping behavior after a maneuver had been conducted. If you had a segment that was that in-between section, then the data points would not be normal behavior, but they wouldn't be an actual maneuver. And then those were causing quite a few false positives. So we changed some of the layers in our convolutional layers just based on the outputs of our models there. One thing that we did notice was that a two-step approach kind of worked best, where we separated it out into if something was a normal operation day versus not a normal operation day. And then if it was a normal operation day, we could kind of discard it, because we could say that this isn't one of the things that we're looking for. It doesn't contain any abnormalities. It is the true, just normal behavior of that satellite in orbit. So we could kind of push it off to the side and say, okay, I'm only going to focus on the things that are abnormal. And from that perspective, if you wanted to expand further, obviously there's various different techniques that you could go into for determining the degree of anomalous identities in the segment that don't belong to normal behavior. And various different ways that you could create additional measurement values to work into your modeling as well. We didn't do that for this. We kind of just, once we identified that it wasn't a normal operation, we applied some follow-on modeling to help us identify specifically which of the nodes within the non-normal operation day were the maneuver, specifically just doing a multi-classification of those different patterns. And I promise this is not all death by PowerPoint. I know that there's a lot of slides here. I was mostly just hoping to kind of frame the challenge itself, what we were presented with working with the MIT ARC lab, and then get to the demo. So now I will get out of PowerPoint and I will actually show our telemap tool. So I did go ahead and load this up because live demos are terrifying, but we have a satellite here. This is one satellite, 6 months. I will say that from what we are used to working with our rotorcraft and aircraft visualizations, we use Mapbox. So you can see here, this is from Mapbox. Mapbox doesn't do so great when it comes to orbital paths. Once you get out to like LEO and GEO, it doesn't do so great. So what you'll notice is that there's like this gap here. What it's actually happening is that as you rotate this, it just picks up. It's like a 2D flat representation of the actual orbit. It just doesn't wrap around or have the arc of the orbit. We are currently looking at various different visualization to build into this. Cesium is one. There's a few other ones that we're looking into to kind of improve the visualization here. But the orbital path is there. It's just not, doesn't have the arc that you would expect to see with it. So once the satellite is loaded in, we have it to, everything's containerized. So the app itself is one container. We also have a modeling app and a segmentation app that are different containers that they all work together in the back end through, like RabbitMQ and all that kind of stuff to, send stuff back and forth and, various kickoff messages. So once the satellite's loaded in, you can actually run this inference pipeline, which will output a few different values here. That was extremely quick, and I do recognize that feels a little, like, oh, that was really quick. What's actually happening is that once the satellite is, kicked in, it does the segmentation, a lot of the pre-work already, so that the inference pipeline itself is just a quick pass through the model. What the amount of data that's getting passed through the model is significantly reduced because, again, that normal operation day data is not accounted for. So once it gets to that first wave of is this a normal operation, it just doesn't send that as that segment as part of the actual inference. Here you can see our inference labels come out as we have them broken down as east, west, north, south. Right, so they're broken down in two different variations. Again, that directionality from the beginning of the conversation that we had. And here you can see that the node itself, we have AD, which is adjust drift, initiate station keeping, and then initiate drift. The CKs are chemical propulsion for station keeping, and then NK just means not station keeping. Again, going back to the PowerPoint, we had that little table there. That's what those different nodes and types refer to. So from here, you can click on any of these. It shows you the points. You can click edit. All of these actually occur pretty much right next to each other. So, as what I'll do is I'll pull up our overview. I wanted to show the edit functionality because it allows you to take a point that was identified as a certain maneuver. If you said that that wasn't the correct point, then you could go in and adjust it. You could also add your own maneuvers. So if you wanted to create a new maneuver, you could just select on the data point. It's very interactive, so you can go in and especially from a testing perspective, if you're reviewing data or you have ground truth nodes that you need to add in, this is a great way to kind of add your ground truth because you can just add it as a label, say this is the ground truth for this type of maneuver, and then you'll be able to visualize it. So what I'll do is I'll go ahead and add a label here, and we'll just call this the DataWorks label. And then we'll pick a nice color for it. Let's do like dark blue. And I hope that that doesn't actually, oh, we'll add a label. Sorry, that was on the update. All right, so I'm going to click a point here, and we'll just add DataWorks, and then we'll give it a nice color. And then we'll add that label in. And so now you can see that that adds that label here. So really, this isn't really the functionality of our modeling or anything like that. This is purely just because I believe in trying to consolidate as many pieces of the machine learning pipeline as possible. So if you wanted to add new labels, add your ground truth, those various different kinds of components that would be necessary to kind of evaluate how your model's performing, you could do that here. Once you have gone through, you can validate these. You can also remove them. So if you determine that one of these labels is not accurate, it's not a maneuver that occurred at all, then you can obviously remove those as well. Here we have our main page for our overview. I'll kind of show off a few of the features here that are really useful for investigating. This is, again, Mapbox, so it's not going to have the best visual here. But what we can do is we can pull the flight path up, and you'll notice that over here, there's these points that kind of refer to our maneuvers. I'll try to get this oriented a little bit better. And so what we can do is if we turn off all of the other points in the data, so these points here, these are just our individual data points for each of those 2-hour bins that are recorded. You can see that there's multiple maneuvers here that are actually being recorded. You'll notice the blue color is one maneuver, and then you'll notice that the pink or magenta color is another. I'll make that a little bit easier to look at. And so you can zoom in, and then we'll go over here to the blue one. So this is our DataWorks label. So that label that we just added in a second ago is here. And then you can come over here, and these are the specific events. Now, on the table here, we have a few different tables that we look at. We can sub these out for any of the variables that we are interested in, but this is really what helps me kind of identify where those patterns are. So as we mentioned, depending on if it's inclination or eccentricity, that helps you identify like which directionality adjustments being made, and that'll tell you like what is the cause of the maneuver. So see here for eccentricity, we can see there's quite a big shift. And if I zoom in a little bit, so what we can do is you can click and drag here. We'll just zoom in on that data point. You can see that the label here, it actually has two labels. So you can see EW and it's ADNK, and then there's a ground truth. So TAC GT is ground truth. And then there's a comma, and then it's EW, AD, and K, which is our prediction. So that's our inference. So they actually landed on the same data points. That shows one that we landed on the data point exactly. If we were 1 or 2 data points off, we could kind of determine what our threshold is for what our error rate that we're willing to accept, and what kind of lag we're looking at. But we can see that it goes from adjust drift down to our next label, which is our initiate station keeping. And you can see there that it also has 2 labels, where it's the ground truth and then also the prediction inference label. So they all landed on the same data point. And when they are the same data point, ground truth and the correct label, you can see they kind of turn this like purple magenta color. If you're looking here, you'll notice that there's an NS ID NK ground truth that is red. That means we've missed that detection in the ground truth. But we do have a ground truth prediction that is NS, or not a ground truth, an inference prediction that is NS ID NK, and it's actually not too far off. We're looking, about 8-ish hours off. I know that sounds like it's not too far off, but considering the segmentation that occurs with these various windows, what ended up happening is we picked it up on a second segment from the behavior in the pattern, but we didn't catch it on the first one. So there's that separation of that 6-hour window that segments is likely what caused us to have this much of a delay in the detection. And then if I revert these back just to their original views, you can see the DataWorks labeled is there. So we can see it visually on the map, and you can also see where it resides in these data patterns. For our inclination, for the north-south, those are the ones that we typically look at for inclination. You can see here that we do have the ground truth nodes for EW, but then we also have, if I can get off, that's EW. Here it is. So our north-south down here at the bottom is our correction that was made for inclination. And then eccentricity, you have hovering over these when they're super zoomed in. So you can see here EW is our eccentricity, and then this inclination is our north-south. So going back to what I mentioned about the directionality being important for when you're looking at these, you kind of identify what's occurring in those underlying patterns. Okay. So I'll kind of pause here. Oh, I did see eccentricity like an ellipse measure. Yes. I will. It's the eccentricity of the orbital ellipse. I'm trying to think if there was like a specific formula or something for it. I can find that, but it's just if you look Google eccentricity of ellipse or orbital ellipse, then that's what it's referring to. So a few of these are various different measurement values that are either produced directly by a component, or they're calculated values that come off of the simulation software, or that we could write, to do your own calculation for. Most simulators that are high fidelity simulators often come baked in with pretty good physics models, and then they have their own calculations that are applied to the data that show things like the inclination and eccentricity that you would use to do the modeling. So I didn't have to create these variables. These were variables that were available through the simulation. Okay. And so that is our telemetry maneuver analytics and positioning platform. Hopefully, through this conversation and through this presentation, I highlighted that we took something that was originally developed, and the modeling behind it that was developed for maneuver detection of aircraft maneuvers, and then we kind of adapted that to meet one of the newer research questions behind space asset maneuver analytics and pattern of life node detections. We think we did fairly well. We obviously have a few different things that we're looking at in terms of applicability here, but I personally, I don't know if it's fair to say I nerd out about this stuff a lot, but this is a huge passion of mine. I think space is incredibly interesting, just in general, and then when you start adding into how do we do trajectory optimization and better forecasting of maintenance scheduling and life cycle management of space assets. I think that it's just a really cool area for AI and space to kind of come together and augment our professionals in these areas.
Hey Chandler, actually, I had a question. It's kind of a simple question. I was just curious, like, have you looked into other interesting AI, ML, data science problems that are taking place in space, and like what some of the companies that we're all kind of familiar with, like SpaceX, are doing?
Yeah, absolutely. And so a lot of the optimization, like I mentioned, into life cycle management, maintenance predictions are all big things. Some of the more interesting stuff are things like how to identify like cyber threats that are occurring on space assets. So if somebody is maliciously attacking your space asset, how do you detect it, respond to it? There's obviously transition from traditional ground-based control systems that everything you have the lag of everything coming back down to earth before it can be analyzed and reviewed, to more of like an edge-based approach where we have things on board the spacecraft that can allow it a degree of autonomy in detecting these things and responding to them. Same thing with collision avoidance systems. Collision avoidance can be anything from computer vision based to other types of sensors that are on the spacecraft that tell it when once a piece of debris or an object reaches a certain diameter, right? What kind of threat is that? How fast is it traveling? All those kinds of things. There's also adversarial interference in terms of like if a satellite is being positioned to block your satellite or to kind of interrupt its regular operation. There's different ways that they measure and detect that kind of behavior as well. So there's a lot of really interesting things that are happening, and we believe that this would be kind of foundational to various different parts of that, which is why we were super excited to participate. Chris, would the
Did you
AI
see?
be able? Yeah, I did. Uh, so that is something that would require a great deal of real-world orbital data to be able to prove out. What I suspect, as with any kind of synthetic simulation type data, is that the answer is yes. So, for instance, for a helicopter maneuver that is produced during in a flight simulator, regardless of how high of a fidelity of the simulator is, how good of a simulator it is, it's pretty easy to train a model that can differentiate between real world telemetry data and synthetically generated telemetry data. And it's usually because certain values in the telemetry data are going to have much less variance. Your rate of anomalous action is going to be much fewer. So if you're up in the air with an aircraft, and this is a funny example that we use with one of the flight schools that we work with. They had a pilot sneeze while he was flying his Cessna, and when he sneezed, he pushed forward on the controls and caused the nose of the aircraft to change. And when you look at it in the data, that kind of behavior would not be reflected in a simulator unless you specifically had to go out and program it. So there's like these little oddball type scenarios, and obviously it's not necessarily, a spacecraft isn't going to be sneezing up in orbit, but it could have any degree of interference or some kind of extraterrestrial type of pull that might cause it to drift out of alignment. Things that a simulator might just not be great at identifying or replicating, rather. Would a transformer architecture be useful in this model? Rob, could you explain a little bit more about what you mean by a transformer architecture?
Here, I'll actually unmute Rob if he would like to just
Yeah, absolutely.
um actually hold on. Can I unmute? Oh, well, he just typed it. The type of
Oh,
technology
okay.
used in.
So considering the similarity that you look at with two-dimensional arrays for like any kind of sequence pattern recognition, it's not much different than what is used for pattern recognition of speech, which is actually one of the first topics that I worked in data science. Was my background as a linguist led me down the natural language processing and parts of speech path. So there are a lot of similarities. It's not something that we tried out with this just due to the time constraints, but I think that it would likely have benefit. Yes, it would at the very least be an interesting experiment.
Is there any other questions? Okay. Well, thank you, Chandler, for the talk. It was very interesting, and I think that did you? I don't know if you put it up there. If you wanted to say it again, like how folks could get in touch with you, either LinkedIn or your company.
Yeah, absolutely. So we have a few different ways that everybody can get a hold of us. Obviously, we have our email is info@axolotl.net. I also want to throw out there, a lot of people when they see the name axolotl, they don't necessarily know how to say it or know what it means. This is actually like a homage to one of my wife's favorite critters. So it's spelled like this. Um, it's a salamander. It's a type of salamander that is from Mexico and South America. They're typically seen in like depiction as pink, but they can be blue and green in the wild, which is obviously our logo is this bluish green kind of color. So she's a real big fan of them. I thought that it was just a cool way for us to, for me to kind of pay homage to her. So our email is info@axolotl.net. All of our links for Facebook, LinkedIn, if you just do axolotl.net/Facebook, it'll actually take you to our Facebook page. And if you go to axolotl.net, this is our website. You can read a little bit more about like our telemap solution, our AeroTrack solution, which is our airborne multi-object tracking. We use a Siamese multi-object tracking algorithm for that. But this is what an axolotl looks like in real life. This is why I pulled up our thing here. But our company's name is actually a acronym. It's Adaptive and Omnilytic Technologies and Labs, so that we can fit into that nice little axolotl acronym.
Yeah, I looked that thing up. It looked like something out of a cartoon or I don't even know, like a cute little like stuffed animal creature. There's these picture of these pink ones that are pretty interesting.
Yeah, the pink ones are the more commonly seen ones or known ones. Those are the ones that people can actually have as pets. Typically, they're only blue and green when they're out in the wild. Pink ones typically aren't seen in the wild.
Very cool. All right. Well, thank you, Chandler, and thank you for everyone that joined. If anyone has any feedback or suggestions for future meetups, feel free to reach out. That includes speakers, anything that you have in mind. But again, thank you for the time, and enjoy the rest of your evening. Thank you, Chandler.
Yep. Thank you, everybody. I really appreciate you tuning in, and thanks, Jason, for the opportunity.
Thank you.